Hi guys, this is a project for Mrs. Bailey's Math Analysis BC class, and today I'm going to teach you how to graph rational functions. So let's get to it. So what is a rational function? Well, a rational function is defined as f of x equals n of x over d of x, where n of x and d of x are both polynomials. I'm running out of space. And d of x is not equal to 0. And that's a basic definition of rational function. We'll see plenty of examples as we move along. So the first thing we need to know when graphing rational function is restrictions on its domain, what our x values generally cannot be. So there are two types of domain restrictions, vertical asymptotes and holes. So vertical asymptotes are when the denominator of our rational function is equal to 0. And to find that, we think, alright, when would our function be undefined? When would the denominator be equal to 0? So to do that, you can take a very simple example here. You take whatever is in the denominator and set that equal to 0. So 0 equals x. And solve for x, which in this case is already done. So we know that our vertical asymptote is at the line x equals 0. So if we were to graph that, remember when you're graphing a function, your vertical axis is not always y. You have to look at what it's defined as. So our vertical asymptote is at x equals 0. And we can symbolize that by drawing a little line. We'll make it green so that it separates. It's right on the axis. So now to see how our graph will behave in response to this vertical asymptote, we need to know what really separates a vertical asymptote from other restrictions on the domain. So a vertical asymptote is where a value of x where your limit, or the value that you get close to as you approach the x value of, in this case, 0, is equals either infinity or negative infinity. So if we were to, and remember, our goal here is to try and graph it so we can get a visual representation of the function. So to graph this, we're actually going to need to see what our horizontal asymptote is. We'll get to that later, but for now, I'm just going to tell you that it's at the line y equals 0. And so we've divided our graph now into 4 sections. Here, 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 and here. They just happen to be the 4 quadrants. So what you need to do is find a value where on one side of the asymptote and the other side. Basically you have 2 separate little sections of the graph in the coordinate system. So you can do that by just plugging in a value for x and see what your output is. So if I say I plugged in the value 3 for f of x equals 1 over 3, or I'm not finding f of x, I'm finding f of 3, and we can see that's 1/3. So I go over and I plot that point to be right about there. There we go. And what's important to keep in mind is that your graph is going to follow your end behavior of your asymptotes. So the graph won't just go, say, in a straight line like that. It won't just cross an asymptote. It can't do that. So we look at where our asymptotes are headed. There's one headed this way and one headed this way. And based on that, you have a picture of what the graph looks like. Now you're not going to be able to plot every single point, but as you learn more about more asymptotes and other points, it will be easier to do this. So then, if we look on the other side of the asymptote, we think, alright, it has to follow its end behavior. So we need to know if it's going to be in this section of the second quadrant right here, or if it's going to be down in this quadrant. And what we can also do, same thing, plug in a value for, so I was finding, say, f of -1, that here, f of -1 equals 1 over -1, and that simplifies, of course, to just regular -1. So I know I'm going to be in this quadrant, and based on that and my end behavior of my asymptotes, can graph that. And that's what the graph of f of x equals 1 over x. Alright, so this one is a little more complicated, not that much, but we look at our denominator and see when will it be 0. Well, x plus 2 equals 0, and x equals 2. So our vertical asymptote, will be at the line x equals 2. And we'll draw that in right now. Go over 2, and draw in that vertical asymptote. And based on that and our other asymptotes that we'll get to later, you'll be able to create a graph of that. And you'll have something on this side, something on this side. But what you're guaranteed is that when your x value gets closer to this x equals 2, your graph is either going to go, say, up like that, or down, but it will approach either infinity or negative infinity. It will get infinitely close. So the next domain restriction we have are holes. Holes are a type of discontinuity. It's when the graph doesn't flow smoothly. But they're called removable. So let's see why. So a hole is basically when something in your numerator will cancel or divide evenly with something in your denominator. So if we take this equation here, y equals quantity x plus 1 squared over x squared minus 1, we can factor that. Just show you a visual representation. X plus 1 is x plus 1. We factor the bottom, we have x plus 1 times x minus 1. And what we'll realize is that you have a common factor in both the numerator and denominator. You can just cancel those right out. What you're left with is y equals x plus 1 over the quantity x minus 1. And you may think, alright, this is great. Find the holes. Well, the hole is your x value that you had here, x plus 1. And you set that equal to 0. So, off to the side, x plus 1 equals 0. You solve for x, you get x equals -1. So on your graph, at the x value -1, there will be a hole. But where is that? Well, what you do is you take the -1 and you plug it into the cancel version to find your y coordinate. So y equals -1 plus 1 over -1 minus 1. That equals 0 over -2, which equals 0. So the coordinate of your hole will be the point -1, 0. Whoops. There we go, -1, 0. And then to graph this, we would continue on like any other rational function. So we'll draw in our axes. And we'll do the same thing. You see, x minus 1 is in our denominator of our cancelled version. And when we set the denominator equals 0, we'll see that our vertical asymptote will be at x equaled value x equals 1. So then, we also can plot the hole at this point. Our hole is at the coordinate of -1 and 0. So we go over -1, 0, and you symbolize holes by an open circle. I'm making that orange so that it stands out a little. But you just draw an open circle where your hole would be. And if you want to see the graph of this, to draw in the horizontal asymptote, which we'll get to in just a sec. It's at the value y equals 1. And if you plug in a value of x that's not the vertical asymptote or hole, and you see what its behavior is like, you'll see that in this section it goes like that. And over here, our end behavior of that asymptote, our end behavior on that asymptote. And as we get to the hole, we simply go around it, and we have this almost perfect curve with this one hole right in that spot, and that's our removable discontinuity. So, and you can have multiple holes. So in this graph, we have the quantity x cubed plus 7x squared plus 12x all over -3x cubed plus 48x. And just to save time here, if you factor that, I'll go ahead and tell you that you'll have f of x equals that. I hadn't factored beforehand, so I had to use a little bit of movie magic. But we look at what our factors are that can cancel. Well, we have a common factor of x. Well, let me make that a little smaller so it's easier to just see it. So you can still see what the values are. And our quantities of x plus 4. Those all cancel. So if we set these values to 0, we have, there's a hole at x equals 0 and x equals -4. And we need to find the coordinates of those holes. So if you plugged in first our x value of 0, we'd have 0 plus 3, which would be 3, or let me use the red pen, 3 over -3 times 0 minus 4, -4, which would be 12, which simplifies to 1/4. And then for our x plus 4, you would plug in -4. So we have -4 plus 3, which would be -1 on the top, over -4 minus 4 is -8, times -3 is 24. So very close to 0. And I'm not going to graph all of this, but just so that you can see it. You still have, of course, on this side, our vertical asymptote at x equals 4. And our horizontal asymptote is actually y equals -1/3, so I'm drawing that a little lower because to show the holes, we'll need to see. So our holes are at -3 and 1/4. I'm sorry, 0 and 1/4. There's a hole right there. And at -4 and -1/24. So very close to our x-axis. I'm sorry, it's a little hard to see, but those are where the holes would be. To graph it, it would look something like that. And on the other side, it's like goes like that. Of course, see the arrows, and you should always label your axes. I didn't, but we'll just move on. So that's it for our domain restrictions. Now it's to our range restrictions, what our y values or outputs could never be. So there's really one type of range restriction called a non-vertical asymptote, and that's broken down further. So to start off with, we have horizontal asymptotes. And horizontal asymptotes are relatively simple. what you do is you take the coefficient of the highest power of x in the numerator and the coefficient of the highest power of x in the denominator, and that's what your horizontal asymptote is. Y equals whatever that value is. So in this one, look for our highest power of x. Our highest power of x is actually just the constant, 1. And in the denominator, we see that the highest value is x squared, our quadratic term. The coefficient is just 1. So when we don't have a value in the numerator, what do? Well, you have to remember that saying 1 is also like saying 1 plus 0 times x plus 0 times x squared, and so on and so forth. But all we care about is that value of the square terms, because we can compare those. So if we take those, 0 divided by 1 equals 0, and that's our horizontal asymptote. F of x, or whatever your output name for your function is, equals 0. So if we were to graph this, we'd then go over and say, alright, we'll have our axes, drop those in. We say, alright, well, first thing you generally want to do is your domain restrictions. So in this one, we check for a vertical asymptote, x squared plus 1, set that equals 0. And if you solve that, you get x squared equals negative 1. To solve for x, you take the square root, but as we know, square root of negative 1 is I, or an imaginary number. It's not real, it can't be plotted on a xy graph. So in that case, there is no vertical asymptote. There is no domain restriction. Your domain can be anything you want. So then we go straight into our horizontal asymptote. Our horizontal asymptote is line f of x equals 0. And so based on that, you have to get the graph. Now, it can be a little tricky to graph, but just to show you what it looks like, that's what it is. And it will get closer and closer to x-axis, but it won't cross it. Alright, so here's another example. First you might be tempted to factor, but that really doesn't do much. None of the factors will cancel out. X minus 1, x plus 1 over x minus 2 times x plus 2. So in that case, we don't really need to factor. To find our horizontal asymptote, we look, alright, our x value of 1, 1's our coefficient here, and 1's our coefficient here. 1 over 1 equals 0. I'm sorry, did I say 1 over 1 equals 0? 1 over 1 equals 1. And that's your horizontal asymptote. So if we were to graph this, h of x, find any of our domain restrictions, which in this case would be at x is positive or negative 2. We'll draw in our asymptotes for that. And then our horizontal asymptote is at value h of x equals 1. So when you have 3 sections like this, it may seem tricky, but it's the same thing. Follow your end behavior, plug in a point to see where you'll be this section, the top or bottom section. And eventually you'll see that the graph looks a little something like this. So slant asymptotes, and this is the other kind of non-vertical asymptote. If your function doesn't have a horizontal asymptote, then it'll have a slant asymptote. So slant asymptotes are are easily identified. So to find our slant asymptote in this, what we first will look for is actually quickly identify whether this has a horizontal asymptote. So we look at our highest power of x in our numerator, see it's our squared term, and the coefficient is 1. The denominator, all we have is 2x. So you have to remember, this is like saying 2x plus 0 times x squared. But then you look at the coefficients, you have 1 over 0, and that's obviously undefined. So your horizontal asymptote isn't horizontal at all. What you have is you have a slant asymptote. So a slant asymptote will look a lot more like just a regular line, and you get that by dividing your numerator by your denominator and taking the result. So time for some good old long division. So there we go. And you should all remember how to do long division, I would hope. But you have 1/2 x for your first thing. X squared. Subtract that, you have 0 for your x squared term. Zero squared plus 0x. And to get that, obviously, we'll say, well, it's not 0x squared, sorry. Basically have 0 plus 0x, and we're trying to figure out what will get us that 0 term. So plus 0, and at this point it's already divided out. And that's your slant asymptote. But this isn't really as helpful without seeing a graph, so I'm just going to have to add another slide here. There we go. And you can see the graph. What was it? H of x is our top. Drawing our axes. You'll see our vertical asymptote will be at the value of x equals 0. And our slant asymptote will be the line h of x equals 1/2 x. Can write that off to the side. That's our slant asymptote. So you graph that just like you would any other line. You have your intercept the axis at 0, 0. Go up 1 over 2 to find your slope. Keep doing that. And that will be your slant asymptote. So to give you an idea of what this graph looks like, if you plugged in your points and all, you get something, whoops, spacing is not right. That looks like this. And you can see that your slant asymptote is right in between those values, your values for which h of x is defined. And that's the basics of slant asymptotes. And remember that slant asymptotes, you don't always have to use long division. In this case, you can use synthetic division. So plug in that value, 6, our coefficients are 1, -5, and 8. So drop that 1 down, 6. That's a positive 1, 6, 8 plus 6 is 14. So you'll notice we have a remainder here. Our slant asymptote would be f of x equals our 1 for our x term, x plus 1 for a constant, and then we have a remainder. So we have to remember what a remainder actually would do. And if you put the remainder in, be plus 14 over the quantity x minus 6. Well, our asymptotes are used to define our end behavior, as x gets either infinitely large or infinitely small. So we have to think, if x is approaching infinity, infinity minus 6 is still infinity. You can just think of it as a really large number. Minus 6 isn't going to do much difference. So then if you have some number like 14 or 12 or 1 even, over some incredibly huge number, it's going to be very close to 0. And same thing if x was approaching negative infinity, it would be very close to 0, except if it was on a number line, your value is 0. As x approaches infinity, your value will get closer that way, and if it was approaching negative infinity, value will get closer that way. But it gets infinitely close to 0, and because our asymptotes are predicting our end behavior, we can actually drop this remainder out of our slant asymptote completely. And if you graph this, your slant asymptote would just be f of x equals x plus 1. And finally, our last topic is intercepts. Intercepts are pretty self-explanatory. They're where your function intercepts the x or y axis. Now you have to think, if your vertical asymptote happens to be something like x equals 0, then your vertical asymptote is the y-axis, and it will never cross there. So your function doesn't necessarily have to have intercepts, but most of the time, or I shouldn't say most of the time, sometimes it will. So to find it, you just remember when your function intercepts an axis, either your x value is 0 or your y value is 0. When it intercepts the x-axis over here, your y value is 0, and when it intercepts the y-axis, your x value is 0. So to find it, it's really simple. You just plug in 0 for x to find your y-intercept, and 0 for y to find your x-intercept. So let's find the x-intercepts first. Plug in 0 for y equals 4x plus 1 over x minus 3. We multiply each side by the entire equation by x minus 3. On this side, 0 times anything is still 0. In this case, the fraction will cancel out and you just have 4x plus 1. And if you solve for x, you have negative 1/4. So then your x-intercept is just the point negative 1/4, 0. I'm running out of space a little there. And then to find your y-intercepts, you just plug in 0 for x. So y equals 4 times 0 plus 1 over 0 minus 3. If you simplify that, you get y equals negative 1/3. So your y-intercept is 0, the point at 0, negative 1/3. And that's it for intercepts. They're another piece of information that you'll be required to give. And that's it. Now you know how to graph basic graphing rational functions. The cases. If you're interested, this video was made using the app Docery. It was super helpful. Loved it. It was very easy to use. And I think it was I would definitely recommend it if you are interested in making videos. It's really quick and it's completely free for iPad or other Apple devices. Thank you very much for watching.